Welcome back to the deep dive. You know, if you're like most of us, you've probably felt that familiar vertigo recently.
Oh, absolutely.
That sensation of trying to keep up with the world of artificial intelligence as it accelerates past comprehension.
It really does.
Every week there's a new model, a new application, a new industry pivot driven by machine learning. And honestly, the information overload can feel, well, a little paralyzing.
It absolutely can. The sheer volume of news has turned the signal-to-noise ratio completely upside down.
Yeah.
The theoretical discussions about AI, they're kind of over.
Right.
We are now firmly in the age of operational AI. We're seeing integrated functional systems that are fundamentally changing core critical industries, not 5 years from now, but today.
Today.
And the challenge for you, the listener, is filtering all that noise to find the truly transformative, actionable intelligence.
And that is precisely our mission here. We've synthesized a really fascinating stack of sources this week. It's a highly focused digest of major AI news, specifically centered around December 7th, 2025. So we're using this as a controlled snapshot, an intense look at AI's transformative power right now, not in some distant sci-fi future.
And this deep dive is designed to go way beyond just the headlines. We really want to extract the core mechanisms and the implications behind these immediate breakthroughs. So we've zeroed in on 4 incredibly diverse yet equally critical sectors.
Which are?
Diagnostics and medicine, real-time safety and automotive mobility, global conservation of the planet, and even the future of entertainment and gaming.
I find that spectrum just astonishing. It really highlights the universality of the technology.
It does.
We're tracking AI as it actively changes the world from these, life and death decisions in a sterile operating room,
Right.
all the way to creating infinitely replayable virtual worlds. It's that duality of serious critical infrastructure on one hand and personalized leisure on the other that shows just how deeply integrated AI has become.
And that universality, that ability to transform vastly different industries, it's all connected by a single fundamental engine. And that's the key insight for our deep dive today.
Okay, so what is it?
What links healthcare, automobiles, rainforest monitoring, and gaming is the unparalleled capability of machine learning systems to identify complex, non-obvious patterns and to handle vast amounts of real-time, unstructured data at a scale and speed that no human
could ever manage.
and no traditional computing system ever could. We're watching algorithmic pattern recognition become the dominant operational force in the real world.
Okay, let's unpack that operational impact immediately then. And there's no better place to start than the sector where superior pattern recognition translates directly into superior outcomes for human life.
Yeah.
Healthcare. So our sources lead with what I consider to be a civilization-level breakthrough.
Yeah.
The development of a new AI system that has significantly improved the accuracy of early cancer detection. And when we talk about significantly, we are not talking about some marginal improvement. We're talking about fundamentally altering the trajectory of treatment and survival rates for millions of people.
That is absolutely the right way to frame it.
Okay.
And to really understand the scope of this improvement, we have to look past the headline and get into the core mechanism.
Yeah.
We are talking about a system most likely built on these complex convolutional neural networks, or CNNs, that was trained on hundreds of thousands of medical images.
Hundreds of thousands.
That scale of training data is what separates this generation of diagnostic AI from everything that's come before.
Let's put that scale into perspective for a second. A highly trained human pathologist, a world expert, right? They might see tens of thousands of highly specific cases over a 30-year career.
So giving them immense depth of knowledge.
Immense depth. But this AI system ingested that much data just to learn the initial parameters of what counts as normal versus abnormal. It's the difference between, studying 1,000 trees and mapping the entire forest.
That's a perfect analogy. And what emerged from that massive, comprehensive training data set is the primary capability that provides the breakthrough.
Which is?
The ability to identify subtle patterns that are consistently missed by the human eye, even the expert human eye, particularly when those eyes are subject to fatigue or, working under extreme pressure.
So we really need to dive into that phrase, subtle patterns. Because a human professional, they're trained to look for known indicators, the classic markers that define malignancy.
Right.
How does the machine see something different, something that brilliant human minds might just overlook?
Well, it really comes down to dimensional feature extraction. So a human clinician looks at a cell and recognizes the specific shape or a size anomaly, a feature that's been codified as a potential danger sign.
Okay, something from a textbook.
Exactly. The AI, however, It's not looking for codified shapes. It's looking for statistical correlations within the raw image data itself.
So it's not seeing a picture, it's treating the image as a massive grid of data points.
Precisely. The CNNs are essentially applying thousands of different mathematical filters to the image. They're identifying what we call feature maps, so patterns in texture, density distribution, cellular structure,
Wow.
and even tiny variations in color intensity or, say, boundary smoothness that are just too minute for us to register as visually distinct.
But statistically, they matter.
They matter a lot. Across those hundreds of thousands of examples, these tiny texture shifts correlate very highly with the progression of the disease.
That's a really important distinction. The AI might be identifying that if the average pixel density in a specific spatial relationship to a cell nucleus deviates by, I don't know, X amount,
Right.
the chance of malignancy increases by 5%. And
Right.
that's a pattern that is just invisible to the untrained or even the trained human eye, which is operating on gross morphology.
That's exactly right.
Yeah.
And because the AI operates without fatigue and with perfect consistency, it can identify anomalies that might only occur in, say, 0.1% of the image's overall data, but which are present 95% of the time in malignant samples.
So it's seeing beyond our limitations.
It allows the system to perceive data beyond human limitations in a routine clinical setting. This significant improvement reported in our sources isn't just seeing what humans see, but better. It's revealing features that we don't even categorize as visual signs yet.
Okay, that makes perfect sense from a technological standpoint, but I have to ask the critical question that I'm sure you, the listener, are thinking about.
Oh, yeah.
If the AI is seeing things that human pathologists cannot recognize, or even label things that don't fit into our current medical textbooks, how do we, as a medical system, establish trust and liability?
That is the central integration hurdle facing AI diagnostics.
Yes,
Absolutely.
right. If the AI flags a subtle pattern and that leads to an invasive, difficult biopsy, and then that procedure turns out to be a false positive based on some unlabeled feature, who's accountable?
And this is exactly why the sources consistently emphasize that this technology assists in diagnostics. It doesn't replace the practitioner entirely.
So it's a tool, not the final word.
For now, yes, the AI's role is as a highly sophisticated alert system. So if the system's confidence level for malignancy exceeds a threshold, let's say 98%, even if the human expert initially sees no major indicators,
It forces a second look.
it forces the human expert to dedicate 10 times the attention, maybe run a new type of scan, or call for a specialist review.
So the AI is reducing human variance. It's forcing consistent attention to these tiny anomalies.
Precisely. And in terms of metrics, this system, according to the Research Digest, improved the area under the curve, the AUC performance metric, by a reported 12% on specific high-risk biopsy samples
Over the established human baseline.
over the human baseline. And for our listeners who track these metrics, that 12% jump in AUC is a massive leap in diagnostic reliability.
Hmm.
It means fewer false negatives.
So fewer cases missed in those crucial early stages.
Exactly.
And that is the ultimate so what? Early detection dramatically increases the chances of successful treatment. This isn't just some academic progress. This saves lives.
It does.
The time saved by not missing that subtle initial sign means the difference between a stage I detection, which often leads to a complete cure, and a stage 3 detection, which carries a far, far heavier burden of treatment.
And that is why healthcare professionals are so optimistic. This shift allows the human clinician to focus their expertise on the complex stuffed treatment planning, patient communication, knowing the diagnostic foundation is instant, tireless, and statistically rock solid. The ultimate promise here is precision medicine driven by immediate diagnostic precision.
It's a remarkable illustration of how scale and consistency applied through machine learning lead to superior life-saving accuracy.
And that very concept of consistent, instantaneous analysis across massive, chaotic data sets is the perfect connecting point to our next topic.
How so?
Well, if AI can successfully analyze the high-resolution internal complexity of the human body, it can certainly tackle the chaotic, high-speed, real-time data flow of the external world.
Specifically our roads.
Exactly. Let's move from individual health and microscopic pattern recognition to public safety and macroscopic prediction.
Shifting our focus from the hospital to the highway. The autonomous vehicle sector has been marked by, let's be honest, bold promises and frustratingly slow incremental progress for years.
For a long time, yes.
But the source material highlights a core breakthrough announced recently. A major industry player achieved a significant leap forward in self-driving technology with an advanced integrated AI system.
And that phrase, significant leap, is really crucial because it signifies the shift away from older, kind of brittle models toward true real-time learning.
What do you mean by brittle?
Earlier autonomous systems were primarily designed using heavily supervised learning. So they were shown millions of images and told, this is a stop sign, this is pedestrian.
Okay.
They got really good at classification, but they failed dramatically at novelty and true decision-making.
So they were essentially rule-based systems with extremely complex sensory inputs. If A happens, do B. But the real world introduces C, D, E, and F all at the same time.
Exactly. And the breakthrough mentioned in the source is the integration of advanced deep reinforcement learning, or DRL.
Okay.
So this is not just programmed automation anymore. The system is explicitly capable of learning from real-time driving data by receiving a reward for successful, safe maneuvers and a penalty for dangerous or inefficient ones. It's learning successful behavior, not just following scripted rules.
So what does that real-time driving data actually look like when you're feeding it into the AI brain? We are no longer talking about static pictures for classification, are we?
No, not at all. We're talking about sensory fusion on a scale that was previously unseen in commercial vehicles.
Uh-huh.
It's the seamless weighted integration of data from LiDAR, gives you precise distance and geometry,
Right.
high-resolution camera feeds for semantic understanding like traffic light color and sign text, radar for velocity and distance no matter the weather, and even acoustic inputs.
Listening for sirens.
Listening for emergency sirens, and this is all processed simultaneously hundreds of times per second.
And crucially, the AI has to weigh these conflicting inputs. A camera might see a plastic bag fluttering across the road, while LiDAR sees a physical object and radar sees movement. The AI has to decide instantly if that object is a threat.
And that is where the DRL shines. It's using the outcome of its past decisions. Did I brake appropriately? Did that action lead to a smooth, safe outcome? To refine its weighting of those sensory inputs. It analyzes millions of driving scenarios to improve its decision-making, especially in those complex edge cases where human intuition normally reigns supreme.
Let's elaborate on those millions of scenarios. Can you give us an example of the kind of unpredictable reality that the old AI models just couldn't handle, but this new system can?
Sure. Consider a scenario in the Pacific Northwest. Heavy rain obscures the road lines. The car in front of you suddenly hits a huge puddle, spraying a plume of water that completely blinds your cameras for a full second.
Okay, that's a nightmare scenario.
And simultaneously, a police officer is gesturing for traffic to stop, overriding a green light. Pre-programmed systems would panic.
They just slam on the brakes.
They'd likely stop abruptly because the camera data vanished, or they'd try to continue because the traffic light is green. Total confusion.
That is the terrifying moment where autonomous technology fails because it can't handle conflicting, messy inputs.
Right. But the DRL system, having been trained on millions of simulation and real-world iterations of this exact type of sensory chaos, learns to heavily weigh the radar, which can still track the car ahead and the trajectory of the water plume.
And the acoustic data.
Recognizing the officer's voice or whistle, plus contextual mapping. It learns that in heavy spray conditions, the loss of vision input is temporary and predictable.
So it doesn't panic.
It doesn't panic. It maintains a smooth, controlled slowdown based on the most reliable remaining sensors and, of course, the officer's overriding gesture.
So it's building a kind of human-like intuition, but it's derived from this massive accumulated experience. It learns to tolerate ambiguity and predict the behavior of others. The source emphasizes that the primary goal is making autonomous vehicles safer and more efficient. So how does this deep learning contribute directly to, quantifiable safety improvements?
Safety is fundamentally about anticipation. Old systems reacted. These new DRL systems anticipate. The AI learns subtle predictors in the environment. For example, it might learn that in dense urban traffic, if a vehicle ahead begins to swerve laterally within its lane by, say, X amount,
Right.
it is significantly more likely to make an aggressive, unsignaled lane change within the next 3 seconds.
That's the automotive version of the subtle patterns we saw in the medical images.
It is.
It's statistical prediction applied to moving objects.
Exactly. The AI adjusts its speed and following distance preemptively based on that calculated probability. It doesn't wait for the blinker to come on or for the car to physically cross the line.
It anticipates the danger.
It anticipates the danger and executes a mitigation maneuver before the risk even materializes. This prediction ability, derived from real-time analysis across millions of data points, is the core safety enhancement.
But hold on. Every single mile driven generates an enormous amount of data. We're talking petabytes flowing back into the cloud. What about the logistics and the data burden?
That's a huge challenge.
If a fleet of 100,000 cars learns a critical new behavior, say a safer way to navigate a new type of intersection, how quickly can that learning be processed, validated, and pushed back out to the entire fleet?
That is the operational challenge that this industry player seems to have solved to enable this leap. The source implies they have cracked the data pipeline and the model iteration cycle.
How?
They are using something called federated learning, which means the data is aggregated and processed on centralized servers, but the initial, lightweight learning can happen locally, right on the vehicle hardware itself.
Okay, so it learns on the fly.
And then, when the central system identifies a truly novel scenario and develops an optimal solution, that refined model is packaged up and deployed wirelessly to the entire fleet, sometimes within hours.
So, a car in Phoenix learns a new trick about handling high temperatures, and that lesson is applied to a car in Helsinki the next morning. That speed of collective learning is what makes it revolutionary.
It democratizes experience. If one car encounters a unique, dangerous edge case, say, a deer wearing a vest walking on a highway median,
Unlikely, but possible.
that experience, once validated, instantly benefits every single car in the fleet. This speed of collective learning is what moves autonomous vehicles out of that theoretical testing phase and closer to reliable mainstream adoption.
And efficiency follows seamlessly from that. If the system is constantly predicting the environment, it accelerates and decelerates with inhuman smoothness.
Optimizing flow, minimizing congestion, reducing fuel consumption, and massively cutting wear and tear.
The shift is clear. The AI has moved past the experimental phase because its ability to handle chaos now consistently surpasses that of previous, more rigid iterations.
That's a huge inflection point for public perception.
Okay, now let's continue with that theme of large-scale prediction and pattern analysis. If AI can predict risks on the highway, ensuring our safety, the same computational power is now being turned toward the greatest long-term risk we face globally.
Indeed. We move now from the controlled chaos of traffic to the sprawling, silent crisis of planetary health.
This is perhaps the most globally impactful application we've discussed yet. The source material confirms AI is now playing a pivotal role in tackling climate change, specifically leveraging machine learning algorithms to monitor and analyze deforestation.
And this is a task that is perfectly suited for AI. It involves remote sensing, massive scale, and the need for an instantaneous response. Deforestation is a global problem defined by billions of data points flowing in constantly from orbital assets.
Let's focus on the data and the scope here. The monitoring covers deforestation patterns across the globe, and it's enabled by real-time data. What exactly is generating this vast stream of information?
It's a fusion of institutional and commercial satellite data. So we're talking about the European Space Agency's Sentinel program, NASA assets, and high-resolution commercial imagery providers.
Okay.
But critically, the AI is not just looking at visible light photography. It's performing what we call multispectral analysis.
Explain that for the listener. How does multispectral analysis change the way an AI sees a forest?
Well, visible light only tells you if a tree is physically missing. Multispectral analysis uses wavelengths that are invisible to the human eye, particularly near infrared.
And why is that important?
It's essential for calculating what's known as the Normalized Difference Vegetation Index, or NDVI. Healthy vegetation reflects very high amounts of near-infrared light.
So a human looking at a photo might see a healthy-looking canopy, but the AI, by analyzing the near-infrared signature, can tell if that canopy is stressed or dying or has been recently cut, even if the leaves haven't fully browned yet.
Exactly. The AI can detect the precursors to deforestation. It can see a road being cleared under the canopy months before it would ever become visible from above.
Wow.
It can spot the subtle thermal signatures of illegal industrial activity or the telltale signs of recent clear-cutting that are obscured by low-hanging mist. The machine learning model filters out seasonal changes, cloud cover, and legitimate agricultural rotation, all things that previously created massive amounts of false alarms to isolate the single relevant signal.
Human-induced environmental disruption.
That's the one.
So that brings us to the crucial operational change here, immediacy. Before AI, conservation was reactive, right? Someone would find out months later that a forest had been cleared.
Right, the damage was already done.
So how does real-time data change the paradigm to proactive conservation?
The time frame shifts from months to hours. When the AI detects a new canopy gap or an NDVI signature drop that exceeds the threshold, it doesn't just record it. It generates an immediate alert,
An alert that's categorized.
categorized by the probability of illegal logging versus, say, natural causes like a fire.
That means actionable insights arrive almost immediately. The data directly helps conservationists take proactive measures to prevent illegal logging. So instead of just documenting damage, they are facilitating immediate intervention.
This is the operational shift. If they know logging is starting now in a specific grid, they can deploy ground teams, they can alert local authorities, or even use aerial surveillance before the operation is even complete.
That's incredible.
And what's more, the AI can integrate audio data from ground-based sensors. Machine learning models have been trained to categorize sounds, so the distinct hum of a chainsaw versus the sound of a farming tractor, for instance.
Providing an immediate auditory confirmation of illegal activity.
Yes.
So the AI isn't just a measuring tool, it's a global early warning and predictive system. What are the critical insights it's giving us beyond just there's a tree missing here?
It's the predictive modeling that is truly powerful. The AI integrates satellite data with all these disparate data streams, like global commodity pricing for specific types of wood, localized weather forecasts, existing infrastructure maps, and even known labor movement patterns.
Wow.
By combining all of these factors, the AI moves from descriptive analysis, which is damage occurred here, to predictive modeling, which says this specific sector has an 80% probability of illegal clear-cutting within the next 72 hours because of high demand and clear operational weather.
That's resource allocation optimization. So instead of blindly patrolling millions of acres, conservation organizations can deploy their extremely limited human and financial resources to the 5% of areas that the AI has flagged as highest risk.
It transforms conservation into a high-tech intelligence operation. The source material emphasizes the role of AI as an indispensable tool in the fight to preserve the planet. And that term, indispensable, suggests that the scale of the global biome is simply too vast and the data too voluminous for human analysis alone.
We can't do it without this technology.
We can't effectively monitor global ecosystems without it.
I understand the massive logistical advantage, but I have a critical question here regarding governance. If the AI detects illegal logging in the Amazon basin, the data is instantaneous and undeniable. But what if the local government or authority is unwilling or unable to act on that information because of political pressure or corruption or just resource limitations? Doesn't the utility of the AI break down if the data can't be translated into enforcement?
That is the essential political hurdle. You're right. The AI provides the insight. It does not solve the sovereignty issue. However, the presence of real-time, undeniable, non-political data fundamentally changes the dynamic. It allows NGOs and international bodies to apply precise public pressure. When the data is instant and verifiable by multiple sources, the window for plausible denial shrinks dramatically.
So it forces transparency.
The AI democratizes the ability to see and to know what is happening, which, in a world of information asymmetry, is the first step toward effective political or economic intervention.
That's a powerful point. The AI provides the light, even if the path remains politically complex. So we've seen this technology applied to saving lives, making roads safer, and protecting the planet. These are heavy, serious, mission-critical applications.
And that universality is what we have to emphasize. The same mathematical power that spots cancer and predicts highway maneuvers is equally transformative in the realm of leisure.
Right.
From the serious work of planetary conservation, we pivot to the lighter realm of human entertainment.
Now I move into the virtual world, which, surprisingly, is often the proving ground for the most complex real-time AI systems.
It really is.
The core application here is that game developers are using AI to enhance player experiences by creating truly dynamic and realistic virtual environments. This is a massive leap from static or even just complex scripting.
It's the move from playing a finely tuned puppet show to interacting with a living ecosystem that genuinely responds to your presence. The breakthrough lies in moving game AI from simple finite state machines, where characters just follow a preset loop, to systems capable of dynamic adaptation.
How exactly are these intelligent systems designed to adapt to players' actions in real time? I mean, what are they measuring?
They are essentially running a miniature machine learning model on the player themselves, profiling their behavior using hundreds of metrics.
Like what?
They track your aggression level, your resource management efficiency, your preferred combat range, your success rate with specific puzzle types, and your tendency to role play versus just power game. And this model isn't just used once. It updates continuously throughout the session.
So if I, as the player, constantly use stealth and target weak points, The AI isn't just reacting to my current action, it's building a profile that anticipates my next one.
Precisely. And then it uses that predictive profile to offer personalized challenges and storylines.
Yeah.
If the AI knows you are a master sniper who exploits line of sight,
Okay.
the next generated enemy encounter won't be in an open field. It'll be in a dense urban environment where your long-range advantage is nullified by multi-story cover and close-quarters combat becomes mandatory. It customizes the difficulty curve and the narrative flow just for you.
That's how it makes each gaming session unique. The environment itself becomes an intelligent opponent or narrator, tailored to expose the player's weaknesses or reward their unique strengths. It moves away from that static game design model, which forced every player down the same tunnel.
And think about the narrative implications, especially in these huge open-world RPGs.
Right.
If you choose to align with a morally ambiguous faction, the AI doesn't just trigger the ambiguous faction ending. Instead, the responses from the non-player characters, the NPCs you interact with, are dynamically generated.
How so?
The AI system might look at the data. Player used lethal force too often. Player stole from friendly citizens 3 times. It then generates an emergent consequence. An initially friendly but heavily moral NPC who previously gave you quests might suddenly refuse to speak to you,
Or even turn on you.
or might even sell information about your whereabouts to your enemies.
So the game is creating truly emergent narratives. Storylines the developer never explicitly scripted based on the consistency of the player's actions. The game becomes a genuinely responsive, emergent virtual world.
That's the core innovation. And this requires using techniques like complex behavior trees guided by reinforcement learning. The NPCs are no longer following a simple if-then script. They are agents with goals, memories, and learned heuristics. They remember if you help them, if you failed a task for them, and if your past behavior profile suggests you are trustworthy or dangerous.
I find that fascinating. This application is often seen as, frivolous compared to cancer detection.
Sure.
But the underlying technological demand is immense. If the AI is managing hundreds of personalized metrics for the player and simulating complex behaviors for dozens of NPCs simultaneously, doesn't that require extraordinary computing power, possibly exceeding what a home console or PC can handle?
That is the significant engineering challenge, the resource cost. And the breakthrough, detailed in the sources, indicates a major optimization in how these AI models are deployed. Many developers are moving the complex, resource-intensive calculation, like the macro-narrative adjustments and the global MPC goal setting,
Off the player's machine.
off the player's machine and onto optimized cloud servers. The player's machine handles the immediate local interaction, while the cloud handles the complex, long-term learning and emergent generation.
So the AI acts as a perpetual cloud-based dungeon master, constantly calculating the next strategic move for the entire virtual world based on player input.
It's exactly that. The primary benefit is enriching the player's experience by providing that unprecedented immersion and variability. This application is actively pushing the boundaries of what's possible in interactive entertainment,
Right?
proving that AI is robust enough to handle the sheer chaos of complex, free-form human interaction in a way that is also highly entertaining.
This section really confirms that AI's impact isn't limited to just critical sectors. It's revolutionizing culture and leisure. It proves the technology can handle extreme uncertainty and deliver specific high-value outcomes, whether that value is saving a life or providing a uniquely engaging evening of entertainment.
It's the ultimate validation that AI models designed to optimize real-world processes can be ported successfully to optimize virtual experiences.
So we've covered 4 vastly different domains in this deep dive: healthcare, automotive, environment, and gaming. And it all stemmed from a single short news digest that defines the operational reality of AI in late 2025.
It's remarkable.
It is truly remarkable how pervasive the technology has become.
It is.
Yes.
And if we synthesize the core transformation here, the common thread running through all 4 areas is critical for you, the listener, to grasp.
Okay.
AI is not just a statistical tool anymore. It's an operational tool that leverages unprecedented data scale. It is identifying patterns too subtle, too numerous, or too fast for humans to manage to deliver specific high-value outcomes.
Superior accuracy in diagnostics.
Verifiable safety and mobility.
Scalable proactivity in conservation.
And dynamic personalization in entertainment.
And in every single case, the breakthrough is achieved by moving beyond rigid programmed rules to flexible real-time learning systems.
That's it.
We moved from supervised learning in healthcare to deep CNNs that see the invisible. We moved from pre-programmed logic in cars to deep reinforcement learning that masters chaos. And we moved from static scripts in gaming to emergent intelligent agents.
That's the definition of the modern AI revolution. It's no longer about theoretical potential. It's about deep operational integration into the mechanisms of our society.
It is already here.
AI is already functioning as a critical component in life-saving workflows, ensuring vehicle safety, monitoring global health, and creating culture today.
The speed of change is astonishing, and the fact that we're seeing leaps forward and indispensable tools in the daily news cycle shows that we are living through the true transformative moment, not just, anticipating it.
Yeah, absolutely. The key takeaway for you is recognizing that AI is an integrated functional tool driving operational improvements in every critical sector. It is optimizing reality using constant real-time data input.
And on that note of optimizing reality, let's leave you with one final provocative thought to consider as you finish this deep dive.
If AI is already proving indispensable in monitoring global ecosystems, processing petabytes of satellite imagery, and accurately predicting the outcome of millions of complex, chaotic driving scenarios to achieve safety and efficiency, what fundamental aspect of daily human decision-making outside of these critical high-stakes sectors will be the next frontier to be augmented, or perhaps entirely governed, by these real-time learning and predictive systems?
Something to mull over until our next deep dive. Thanks for joining us.
Thank you.